My name is Christopher Lusick, and this is my video lab report for Lab 3, Black Hole. For this lab, I developed the following problem statement: how to determine the mass of a black hole using the known mass and trajectory of a star orbiting around it. The answer to this question is important because it will help us to understand Newton's second law using parallel and perpendicular directions and Newton's universal law of gravitation. To complete this lab, I'll use these laws and GlowScript to create a computer model. First, I will explain Newton's second law in relation to this lab experiment. As shown in the momentum principle, F net equals the derivative of momentum with respect to time. On curving paths, Newton's second law states that F net is equal to the forces in parallel direction plus the forces in the perpendicular direction. This concept is shown in the model to the right. Newton's universal law of gravitation helps us to calculate the force of gravity between two objects. The force of gravity will be the net force in this experiment, as is the only force acting on the star. My procedures for this lab were to download the starter code for Lab 3. I inserted my email for unique star trajectory and then inserted formulas that could be used to solve for the mass of the black hole. This process will be explained in further slides. These models I have created are very helpful for understanding Newton's second law in relation to this experiment. As shown in the models to the right, the net force always points towards the black hole, while the force perpendicular always points towards the inside of the path and is perpendicular to the parallel force. This shows that the parallel force changes the speed of the star, while the perpendicular force changes the direction of the star for a curved path. The models also show that when the star is closer to the black hole, the gravitational force is larger as there is less distance between them. This means that the star will have a greater speed when it is closer to the black hole, as the force of gravity will be larger. With this information, I am almost able to solve for the mass of a black hole. I now just need to manipulate the formula for Newton's universal law of gravitation. As shown, this can be manipulated to solve for one of the masses. This mass, m2, will be the mass of the black hole in this situation. The mass of the black hole will be equal to F net times r squared divided by g times m1. In this formula, F net is the force of gravity, m1 is the given mass of the star, r is the distance from the black hole to the star, and g is the gravitational constant. I then edited the code to input the mass of the star and input Newton's second law to solve for F net and its components in the perpendicular and parallel direction. I also put input delta t to be 1 day, or 86,400 seconds. Using F net equals dp dt, I was able to input formulas for the different components. I then manipulated the equation for the universal law of gravitation to solve for the black hole mass, shown here. When I click Run, the computational model of the star orbiting the black hole is shown. You can see how when the star gets closer to the black hole, the forces, shown by the arrows, increase and the speed of the star increases. Therefore, it also slows down towards the end of the path as it is further away from the black hole. The code also prints the calculated mass of the black hole at each time step, shown here. This took me to the results of my lab. I took the average of these 536 calculated data points and found the average mass of the black hole to be 9.80 times 10 to the 33rd kilograms. Improvements to this lab could make a model so that there is less variation in masses. Also, I could use the calculated average mass to make a model of this situation and input this mass. I could then compare these two models to see how accurate the calculation is. I then answered the question, what does it mean? This lab helps us understand that the net force and its components are different from the rate of change of momentum and its components. We can solve for the rate of change of momentum using the given information. However, we cannot solve for or measure the force between the two objects because we do not know the mass of the black hole. We must assume that these are equivalent in the model and solve for the mass this way. I then answered, what if the mass of the black hole was changed, but the star's trajectory stayed the same? If this happened, we cannot solve for a new mass. This is because we used the F net, the momentum principle, to solve for the mass in the formula for the law of universal gravitation. As the mass of the star and the motion are unchanged, g, r, and F net are also unchanged. This means that the result would be the same mass for the black hole through this process, even if it was a different black hole. Using Newton's second law and the law of universal gravitation, I was able to calculate an average mass for the black hole given the information in this lab. This black hole is roughly 9.80 times 10 to the 33rd kilograms. This concludes my video lab report. Thank you.